Hello, everybody. So we've got a couple of quick things to finish up with the fundamental theorem of calculus, which is what we had been working on previously. So I've still got that up on the screen there. We've talked about it quite a bit. But I want to make a couple of comments before we move forward. So just want to first of all point out, all right, there's two, we've got these two parts that both really have to do with the connection between integration and differentiation. But I want to make really clear that when I write something like this, oops, I don't like how that one looks. Let's try that again. When I write this symbol or a collection of symbols versus writing this symbol or a collection of symbols, right? These are two very different things, even though they look very similar. This here, right? This produces a function, right? When we've computed one of these, we end up with a function, right? An antiderivative. And when we've computed one of these, we end up with a number, which represents the signed area under a function, right? The functions and numbers, right? Unless it's a constant function, they're very different things. And even when it's a constant function, we're still thinking about it as quite a different thing. So we have to be careful as we move forward, right? It's usually not a problem when we are, say, computing something. We compute the right thing more often than not. But sometimes when we're kind of working abstractly, it's really easy to mix up which one of these we should be talking about. Okay, a couple other things. Let's do an example, right? So for instance, when I write this, right, this is an example of the antiderivative, the indefinite integral, which produces a function for us. And we went over this one before. The absolute value of, the natural log of the absolute value of x is the antiderivative for 1 over x, okay? One thing we didn't say that we should is, I mean, this really goes as is kind of the convention in mathematics always when you write a function. If you're not restricting the function in any particular way, we think of it as some particular interval for which this is defined. And so in this case, for instance, the domain of the function I'm producing is x not equal to 0, which is also the domain of the function in the integrand. They don't always have to match perfectly. You can have functions that have problems sometimes. So we'll see some examples of that as we go on. But in this case, they do, right? Both of these are defined for all real numbers except for 0. I also want to introduce a little addition to this notation, right? So if I were, for instance, to evaluate this integral, do the definite integral of 1 over x from 1 to the number e, right, what do? We look for, right, so if I have my antiderivative and, oops, from a to b, and I'm looking for f of b minus f of a, right, there's kind of two things I have to do. I have to find this antiderivative f, and I also have to compute it at these endpoints. So this notation just gives us a convenient way to do one of those things at a time. I can look at this and first just think, what is the antiderivative? Well, we just found this, and in fact, I don't need the antiderivative. There is no such thing as the antiderivative, but an antiderivative. I'm going to take the simple form. I don't need that constant. But remember, I'm supposed to be producing a number, and what I've written is a function. So we have this other notation. We draw a long vertical bar. I've also seen it done with these little things. I've seen both done. So my habit is to do the vertical bar. I'm going to stick with that one, but there are plenty of people who do those little elbows on the end. And we just put the two values, 1 to e, okay? And this just means the function in front of it, or the thing in front of it, evaluated at these two endpoints and subtracted, right? So this would be like this. Natural log of e is 1, natural log of 1 is 0, so this just equals 1. Okay, so in total, what I would say is just in general, and this isn't only useful for integrals, but as in general, you'll see people write things like f of x from a to b just means f of b minus f of a. There's also another time we use this. If you recall from, or a similar thing, you may or may not have seen this before. If you recall in differential calculus, right, if I have a function f of x, I can write f prime of x, right? If I want to write f prime of x, or f prime evaluated at a point, or the function evaluated at a point, that's easy enough to do. But we also have this notation for derivatives that doesn't really give us a place to put in where we're evaluating it. Sometimes people do something like this, again, this vertical bar, and put an a next to it. So we won't be using the one with the derivatives so much. We will be using this one quite a bit, the one with the one I used up here quite a bit. And so I just want to point that out. And it's a nice notation. It lets you separate that process out of starting with finding the antiderivative and then computing the values without having to jump straight into the computation. All right, couple more things. The rest is a little more I don't know what the word is. I'm struggling for the word right now. So let's just jump into it. We're gonna talk about something called net change, and this is really quite simple. It's really not much of a new topic, just a way of thinking about something we've seen before. One way we can think about the fundamental theorem of calculus, the second part, is that if I take a function that's a derivative of another function, so I have a function capital F, I put its derivative into my integral, well, this is very simple to evaluate. We already know the antiderivative of the derivative of f. The antiderivative of the derivative is the function f, right? And so, but look at what this is saying. If this is a derivative, we can think of a derivative as a rate of change. It tells us how f changes. If you integrate over this rate of change, what do you get? The value at the end minus the value in the beginning. In other words, the net change. And that's the idea we want to say here, that just the integral of a rate of change, and I guess I should really say the definite integral of a rate of change is the net change, right? And we've already seen this when we integrate over a velocity. We take the difference in the positions at the endpoints over which we're integrating. What's the overall change in position? What happens? And velocity is nothing but a rate of change of position, right? And this works. This is the exact same thing we have up here because x prime of t is equal to v of t. Okay. So let's do one more example of that kind of a thing with something that's not velocity. We tend to use that example a lot. It's a good one, but let's try to use something else for a change. So here I have a function that I've already written out. H of t is going to be the tide level in meters, okay? So the way I've written it, I'm assuming there's a tide that has a midpoint and then it has a high tide and a low tide. And according to my function that I've written, it goes 8 meters above and 8 meters below the high and low tide. It has a period of 24 hours. So my input t is in hours and my output is in meters, okay? And I have no idea how realistic this thing is. There's probably somewhere in the world that has a reasonably close approximation to this. And then I've computed its derivative, right? So just a simple derivative. So first I wrote what the derivative would be. H prime of t is the rate of change of the tide level, meters per hour, right? So at noon, maybe the tide's increasing at some rate. At 6 p.m., it might be increasing at a different rate. And then I computed what that is algebraically, and I got this 2 pi over 3 cosine of pi over 2 function, okay? So let's just make a couple of comments here, or a little bit of an example. First of all, notice if I am to integrate over h prime of t dt. So I'm integrating over a rate of change. I simply take the value of the height at the end of the interval minus the value of the tide height at, or the level of the tide at the beginning of the interval, and this gives me the net change in the tide. Right? Net change means it doesn't matter what happens in between. So for example, oh, sorry, I want to mention, I have a graph here of this function. So I've just shaded in two areas. So if you look closely, this is going from, let's turn off some of these grid lines. This is going from 0. All right, so here is, oops, I guess it won't let me draw on top of that. But it's going from 0 to 25. Or to 20 to 24 is one complete period. I've shown a little bit extra on the edge. But if you look at this blue hump and then the red valley, that's, you know, starting at 0, the tide increases to its max, comes down back to 0, decreases, comes back to where it started. Okay, so that I just have there to help us. We'll talk a little more about it in a minute. Okay, so let's notice what happens if I integrate over h prime of dt over a 24-hour period. I get h of 24 minus h of 0. Just plugging in these numbers to the function h up here, I've got 8 sine. Putting 24 in, I get 24 times pi over 12 gives me 2 pi minus 8 sine of 0. Those are both 0, and we end up with 0. Okay, right? That's the net change. It doesn't care that we went up 8 meters, down 8 meters, down more 8 more meters, back up 8 meters. The tide has done quite a bit during that time, but it adds up to nothing, right? It adds up to nothing. If we do something like, let's do another one, 0 to 18 h prime over t dt. This is going to give us, let's see, h of 18 minus h of 0. We already know h of 0 is 0, so I can just ignore that piece. H of 18 is going to be 8 sine 18/12 pi is 3/2 pi, which is a -1, so I get -8 meters. Right? Again, looking at the graph, this is starting at a tide in the middle, going up 8 meters, down 8 meters, and then down 8 more. But all we get in the net change is that -8. Okay? So that's what net change means here. Okay? Sometimes, though, we want the total change. Okay? So let's see. Let's bring this graph with us a little bit. Just going to move this down a bit. Let's look at the total change. And, well, I'll just rewrite the function when we need it. All right. So in the total change, what we want to do is ask ourselves, maybe, for instance, I know nothing about boating, so I'm going to say something probably ridiculous here. Maybe you're keeping your boat in a marina or in a dock anchored somewhere in this tide, and you're worried about the wear and tear as your boat's going up and down with the tide, right? Maybe, whatever, it was an emergency and you had to do the little chain to the anchor. I don't even know if that's a real thing. And it's rubbing against something because you're in an emergency situation. So you're worried about how often it's going to be moving up and down and how much sort of length of chain is going to be rubbing against the ship, damaging it. Okay, so you don't care if it's moving up or down. You don't want up to cancel out down. You want them both to count. Okay, well, what means we should do, instead of, let's say we want to see how much happens over the course of a day, we're not going to do this integral. We just did this one and saw that it was 0. The problem here is that sometimes this is negative and it it subtracts from what the positive did, and we want to end that. How do we take things that are negative and make them positive? Absolute value. Okay. So now we've got to figure out how to integrate over absolute value. Okay. Well, here's the trick. So here's what we're going to do. H prime of t let's see, h prime of t was equal to 2/3 pi cosine of pi over 12 t. Okay. So when we look at absolute value of this, we have to write this as a piecewise function. Okay, so what does that mean? So let's sketch ourselves a little graph of this. Let's see, cosine. I'm going to sketch a quick graph. Cosine starts here and ends here after one period. So in this case, the period is 24. Let's mark off 12, 6, and 18. So our cosine graph is going to look like this. All right, so I missed that one spot, but you get the idea. There, that looks a little better. All right. So it has the zeros here and here. It's negative between 6 and 18. It's positive otherwise. So what does that mean? Well, when it's positive, it does nothing. So it just leaves h prime alone if t is between, or let's say, yeah, I'll do it this way. If t is between 0 and 6, or t is between 18 and 24. And we can also look at, and then when t is negative, how does it make it positive? It just multiplies it by a negative. And this is going to be for t between 6 and 18. Oops, I got to get rid of those, or equal to. It can't be both of those. Okay. Right, so what does that do to our function? Well, the new picture is it does nothing to it in these places where it was already positive, and where it was negative, it looks like this. Okay. And so to compute this integral, we have to split up the integral into 3 different integrals, because they're different functions on each of these intervals. For instance, we're going to have 0 to 6, h prime of t. This is the continuation of this, dt, plus 6 to, what was it, 18 of negative h prime of t dt. Let's just take that negative outside and make this a minus. Plus 18 to 24 h prime of t dt. Right, so we're going to split it up into these 3 integrals. Each of these we already know how to solve. This is going to be, this first one is just h of 6 minus h of 0 minus h of 18 minus h of 6 plus h of 24 minus h of 18. Right, there are my 3 integrals. Right, using the net change theorem on each of them. All right, so let's compute this pretty quickly. Let me remind us of what h was. H, remember, was H was 8 sine of pi over 12. And actually, we can do a little bit of algebra first. We're going to have h of 6. I remember that h of 0 was 0, so this one goes away. H of 24, I remember, was 0 from earlier work, so those two go away. I have a minus h of 18 and another one, so I'm going to have minus 2h of 18. So I've got those two, and I've got plus 2h of 6, because this one here becomes a positive, and I've got a positive there. So, oops, I just need a 2 here. I need to write that again, sorry. Okay, so this is what it works out to. And when we compute this, we get, let's see, 2 times, it'll be h of 6, which is 8 sine of 6/12 pi, minus 8 sine of 18/12 pi. Oh, we did that one already too, I forgot it. And what do we get here? 2 times, so 6/12 pi is pi over 2, sine of pi over 2 is 1, so I get 8. Sine of 18/12 pi, or 3/2 pi, is negative 1, so I get positive 8. So I get 8 plus 8 is 16, times 2 is 32. Okay, so notice how different it was. When we did the 0 to 24 without the absolute value, we got 0. Now we got 32. Let's see what that's accounting for. Let's look at our graph. So if you look at the graph here, right, along this edge, right, as the tide goes up, we gain 8 meters. Then we lose 8 meters. Then we lose 8 more meters. This is, remember, our position function. And then we gain 8 more meters to end up where we started at. However, all we care about is the movement. So we counted all of these. 8 up, 8 down, 8 down, 8 up, right? And so in the end, we're ending up with a total of 32 meters. So if you're thinking about that chain rubbing against the ship in that ridiculous example, it means 32 feet of chain have now kind of crumbled some edge of the ship or something. Okay, that is it for this one. Thanks, everybody. I will see you in the next one.